Hello friends, welcome to my YouTube channel. Today we'll see the another example of mixing chamber. In my previous video we have seen the various geometry of a mixing chamber where we have the different position of inlet. Also in example 2 we had seen that two inlet at inclined positions. This time we will see two inlet at horizontal positions, and we will see the how flow pattern will change. Intention of taking different geometry is that we have to understand if we change the inlet positions or geometry, then it affects on the flow patterns. So let's get start with the Ansys Fluent. First we will call the geometry. Just drag and drop on the project schematic. Right click and import the geometry. I have created a geometry in Creo. Just right click and open in design modular. Open in space claim, but my preference is design modular because I work a lot on design modular. It will take time to open the design modular. Once it is open, we have to generate, and we will define the inlet 1, inlet 2, and outlet, wall, and symmetric. Yeah, now it is open, so just click on generate. So our model will loaded. Yes, go to the view and just off the frozen body, so you have the clear image of model. If you see the model, it is the half portion of mixing chamber because of the symmetricity. And we have one part, one body, that is our domain, fluid domain. Next step is to define the inlet, outlet, and wall. So in selection filter, select on the face, right click on this face and say name selection, inlet 1. Say generate, inlet 2, this will be our outlet. This is our symmetry plane. Yes, and the rest of the portion will be our wall. Okay, just right click and say wall, click on generate. Yes, now you can see in the outline, tree outline, we have the inlet 1, inlet 2, outlet, symmetry, and wall. So we have done with the design modular. we'll save it, and we'll return to the project schematic. Before that, just save the design modeler. I will save on my local drive. Mixing chamber. Yes, now next step is where to create a mesh. So for that I will drag the mesh and attach to the geometry. Just double click on the mesh. It will take time to open the mesh environment. Yes, now you can see in the outline already we have defined the name selection, so it will come here, and just click on the mesh, and in the mesh details we have to change the physics preference to CFD, and the relevance center should be high. Then in the sizing we'll change with the proximity and curvature. Relevance center should be fine. Transition should be slow, and in the quality we'll on the orthogonal quality, so we'll know the minimum, maximum, average and standard deviations value here. In inclinations we'll take a program control, and we have set the maximum layer 5 of increment 1.2. You can manually also select the inlet boundary or outlet boundary where you required the boundary layer. Then just click on mesh, right click and generate mesh. We have the fluid property and boundary condition for inlet and outlet. So for the fluid we have the water, and density is given 1000 kg per meter cube. Viscosity is given, conductivity and specific heat is given. Also they have given the Reynolds number for inlet 1 and inlet 2. Based on that we come to know that the flow is laminar or turbulent. And for the inlet 1 we have the velocity 1.2 meter per second and temperature 20 degree. Inlet 2 we have the 2.5 meter per second and temperature 40 degrees Celsius. So we will set this value in boundary conditions. Yeah, now you can see we have very fine mesh. And you can see the layer. See, we have 5 layers. 1 2 3 4 and 5. If you take the cross section, you can see the layer. So we have done with the meshing. We'll save it and we'll move to the pre-processing. I will close meshing environment. Now we'll attach the Fluent to the mesh, but before that we have to update the mesh. Our problem is three-dimensional, it is not a 2D, so in a setup it will detect automatically as a 3D. Just double click on setup. Yeah, as I mentioned that in dimensions it detects 3D, and here we will take a double precision and we will keep rest of the option as it is. Say OK. Yes, then first step is we have to convert the unit for a temperature. We'll select degree Celsius, and our solver type is a pressure base. It is not a density base because density is not going to change, so we'll use a pressure base. And it is a steady state simulation, so we have selected study. In model, as I mentioned in problem description, that we have the Reynolds number. Based on that, it is a turbulent flow. Before that, just on the energy equations, because we have to see the heat transfer also. And instead of laminar, we will select the turbulent model, that is a k epsilon, k omega that we have. And we have defined the boundary layer, so we'll go with the enhanced wall treatments options. Say OK. Yes, we have defined the model. The next step is material, to add material. So we need a water, so we'll create a material. Material should be fluid, not solid. And just click on Fluent database. In the material list, just select one and type W. Water liquid, say copy and close. Before say OK, we will change the values, that is we have 1000 here, and for a specific heat we have 4216. Thermal conductivity is 0.67, and viscosity okay. Now we have set the fluid. Now you can see in the list we have the water liquid here. Most important thing is the sail zone. We have one sail zone, that is the fluid domain, our mixing chamber. And if you say it should be a fluid, not a solid. And next step is the boundary condition. So in the inlet, just double click on inlet. We have the velocity 1.2, I think, yes, 1.2, and temperature, turbulent intensity is given 5%, 20 degrees Celsius, say OK. And for inlet 2, you can also copy the inlet boundary if it is same, but in our case it is not same, so I will enter the value, and 40 degree. Okay, outlet should be pressure, gauge pressure 0, and we'll keep as it is. In symmetricity it will take automatically symmetry zone, and for wall we have to change stationary because it is not a moving wall, so we'll keep as a stationary wall. Actually we don't know the body temperature of mixing chamber, so we will not mention anything here. Otherwise we have the option, we can provide the heat flux temperature. It's the same actually. Now we have defined the boundary condition. Now next step is solution. In that we will choose the method, that is the coupled. It will converge fast if we go with the coupled instead of simple. For a gradient, take a least square cell base. Pressure should be a second order, momentum second order. Keep rest of the option as it is, and in the control we can also add some report. We will create a new report for a surface at area weighted average for the outlet. We'll say outlet report outlet area weighted average, and we'll choose temperature and static temperature for the outlet, and also we'll create a report file and we'll plot with the frequency, or we can say the iteration, 3 iteration. After every 3 iteration it will plot. Print to console, then create. OK, now you can see we have created one. Also we will create one more for pressure outlet, and select area weighted average, and here we will take a pressure and static pressure to the outlet and keep this option on. Okay, in the report now you will see we have 2 reports. In the monitor also we have 2. In the plot also we have 2. So it will once when we run the simulation, it will show you the plots. Now next step is calculation activity. In the run calculation we'll mention the iteration, that is the 150, and before that we have to initialize we'll go with the hybrid initialize and we'll say initialize. Yes, hybrid initialization is done. Then we'll go to run the simulations with 150 iterations and we'll say calculate. In the console it will show you the progress. Yeah, as per the convergence criteria, uh, it has to go till 10 raised to minus 3, and for the energy equation it has to go 10 raised to minus 6, and after that it will be a constant value. So based on that we can say our problem is converged. Also you can check the flux report and you can see the unbalanced quantity, and as we have set the report outlet area weighted average of temperature for the outlet and pressure at outlet, so it will be changed. It will take time. I will come back once the solution is done. Hello friends, welcome back. Now you can see our calculation is completed, and in the console you can see calculation is completed, and now you can see the continuity equation goes down till 10 raised to minus 3, and after that it is the same, and energy equation till 10 raised to 6. In the report outlet we have the average temperature at outlet, that is 307 Kelvin. After the iteration 50 onwards it is a constant, and 0 to 50 we have some variation in the temperature, and pressure as we have set the 0, so it's showing the straight line. Okay, the next step is we'll see some result, and we'll go to the graphics and we'll say contour. We'll check the velocity contour first. Take the field and select here velocity and velocity magnitude for the symmetry plane. On symmetry plane it should be a smooth coloring. Say display. Go to the viewing and just off the lighting, so you will have the clear picture. Now you can see in the velocity field we have given inlet 2 as a velocity 2.5 we have defined, so based on that you can see the results, and for the inlet one we have given 1.2. Next we'll see the temperature distribution in the mixing chamber. Symmetry plane. Here you can see at inlet 2 we have given 40 degree Celsius, and inlet 1 we have given 20 degree Celsius, and the rest of the portion in the mixing chamber we have temperature in between. You can also check the pressure throughout the mixing chamber, static pressure at symmetry. Now you can see at inlet 1 we have the maximum pressure, and we can see the vector also. Just click on the vector, and here we will take the velocity and velocity magnitude at symmetry plane and say display. You can increase the scale. We'll reduce little bit by 10, 5. Yes, now you can see the flow pattern, how it flows in the mixing chamber, from the inlet to it flowing. Yeah, now you can see here, and from the inlet one it is on the only top side of the mixing chamber, and we have the swirl here also. Yes, now you can see. You can also set the path line for the velocity and velocity magnitude at symmetry planes, and it is continuous for the zones symmetry display. It will take time little bit. Yes, we'll reduce the step. And you can see the pulse. It will show the how the fluid is flowing. Say stop and close. In the plot, XY plot, we will see the temperature at outlet. Save plot for I think we have to change the directions. Red one. Yeah. Yes, so we have seen the post processing, and in the result we have seen the contour for the pressure, temperature and velocity. So you can see if we change the geometry or we can change the boundary conditions or location, so it affects the flow patterns. So it is very important if you are doing any study on the flow patterns, you must have to consider the orientation and location for inlet and outlet. Yeah, that's it from this tutorial. We will see the next tutorial. In that we have a different geometry, and I will show you the next example. In next example we have two inlet at top. So here also we have changed the geometry. It means our flow pattern will also change. We will see this in a next tutorial. If you like the video, please press the button like, and please subscribe my channel. Thank you very much.